Hello, our senior design consists of a 3D printed surgical implant to treat pelvic organ prolapse. Our advisor and liaison is Dr. Mathias Brieu, and the mechanical engineering students are Eduardo Gonzalez, Abdu Kaoussarani, Gustavo Medel, Casillas, and myself, Catalina Lee. We are now going to go over the background, problem, and objectives of this project. Human organ prolapse is a disorder in which the pelvic floor tissues are not able to adequately hold the pelvic organs in place. These organs include the uterus, bladder, vagina, small bowel, and the rectum. Any stretching or weakness in the uterosacral ligament, which are supportive structures that attach the cervix to the sacrum, will lead to pelvic organ prolapse. There are many factors to developing this pathology, such as obesity, constipation, pelvic organ cancers, and the most common factor, childbirth, mainly through vaginal delivery. Pelvic organ prolapse affects roughly 50% of Paris women, that is women who gave birth naturally, and around 37% of women 60 years and older. Here we have a depiction of the various stages of uterine prolapse, which is the prolapse of the uterus. Stage 1 consists of a mild prolapse in which the organs rest on the upper vagina, but are still supported by the pelvic floor. A stage 2 prolapse is when the organs have fallen, but are still contained within the vagina. The more severe stages involve the organs protruding beyond the vaginal opening, which is at stage 3, or completely through at stage 4. Available treatments for pelvic organ prolapse are pessary, pelvic muscle therapy, and surgery. A pessary does not fix the issue. It just consists of a device which is inserted into the vagina to hold the organs in place. Pelvic muscle therapy is only helpful to those with mild prolapse. Sacrocolpopexy consists of a surgical implant which holds the organs in place. Unfortunately, this treatment usually lasts around 5 years. Current implants have failure rates that are reaching 40%. This is due to the materials used, such as polytetrafluoroethylene and silicone, which have shown to be toxic to the human body. Another issue is that the geometry and materials used are not patient-specific. And as shown on the previous slide, there are various stages of pelvic organ prolapse. Therefore, a solution to this is in manufacturing 3D printed implants, which can be made in a clean room environment using biomaterial filaments to create patient-specific meshes. Therefore, the objective of this project is to obtain the stiffness range of healthy pelvic tissues, as well as 3D print the prototype using a safe biomaterial. Since the stay-at-home order was still in effect during the beginning of this semester and COVID-19 cases were rising at the time, we were uncertain if the campus testing resources would be available to us, which is why we decided to build our own tensile testing machine for this specific prototype. And so the objectives are also to build a tensile testing machine that provides displacement and force feedback to test the implant prototype's stiffness. And now we will discuss the overview and requirements of this project. Human pelvic tissues are anisotropic, meaning that their physical properties differ in loading directions. There is a small amount of research involving human female pelvic tissue properties available. And of those that are available, the testing that was used was uniaxial loading, which is helpful, but the uterosacral ligament goes through multiaxial loading. There is only one published paper that involves biaxial loading. And so to be able to determine the uterosacral ligament properties, both uniaxial and biaxial loadings were compared. We were able to obtain the raw data of the biaxial loading tests and focus on the subjects that do not have pelvic organ prolapse because we need to construct a device that imitates these healthy biomechanical behaviors. In order to obtain the stiffness, we focus on the slope of the curve, primarily the one in the largest strain, because we do not have enough information about the tissues to confidently analyze the low strain data. This is shown as the blue data points in figures 5 and 6. Unlike tensile testing of rigid materials, these tissues were subjected to loading that is not in the direction to the material's weight. So in order to compensate any sagging due to the tissue's own weight, the tissues needed to be stretched at some point, which is why we cannot confidently analyze the low strain data, which is shown in red. The slopes in both X and Y directions of the 11 non-pelvic organ subjects, pelvic organ prolapse subjects, were analyzed and compared to the large strain uniaxial test. And from there, we determined that the range of stiffness of healthy uterosacral ligaments lies between 1.9 and 6.3 megapascals. The requirements for this project are having a biopolymer that is 3D printable with a structure that is anisotropic, and to build a tensile testing machine that provides force and displacement feedback with minimal manufacturing due to our limited resources. And now we will discuss and now Abdu will discuss the uniaxial testing machine design.
Hello everyone, my name is Abdu Kaoussarani and I led the mechanical design and assembly of the uniaxial tensile testing machine. Here on the right in figure 5 was the version 1 concept design of the test machine that was designed in Autodesk Fusion 360. All major components of design are labeled and listed accordingly to the left. This preliminary design was simpler than the finished product, which I will show you in a few slides over, but featured most of the important components needed to successfully reach our goal with the machine. The idea here illustrates that the motor, part A, will be powered to spin a lead screw, part K, which shall translate the housing block with a grip attached on top, here seen as part D, which holds the specimen illustrated in red for tensile testing. Behind the specimen is a load cell labeled J, which shall provide data once pulled on. The grips were not yet designed in the first iteration of the machine, as focus was put on proof of concept of the machine itself first. So now that we have an idea of how we wanted the machine to operate, I'd like to share the goals of the machine, which are 1, to predict performance of the specimen that is being tested under normal and extreme stresses, 2, to make absolute that the requirement of the printed specimen are being fulfilled, 3, to demonstrate a proof of concept that a 3D printed surgical implant can be a resourceful option, 4, to provide data, and 5, as a means to provide comparison information between other printed options. Next, we have part 1 of the design process, where the parts here listed are the ones that needed to be purchased since they could not be reliably manufactured outright for the machine. These parts include a triple 20 by 20 by 20 extrusion rail for the machine and components to be bolted to, a linear guide rail with carriage, a ball screw kit, which included both supports at the end, a coupler and lead screw itself, an emergency limit switch to stop the machine, and finally, an adequate load sensor. Now, dimensions and specifications of these parts are also listed above. The only components listed here that are revisions from the original concept design are the black end supports, shown in figure 8. A floating bearing support was added to the left of the machine, and a fixed bearing support was added to the right to reduce moment and frictional forces on the middle housing, which bears the weight of the grip, the specimen, and the aluminum block. Next are all the components that had to be designed and manufactured. These parts include revisions from the original concept design and were all made in Fusion 360 to then be printed by our teammate Eduardo, who owns a 3D printer. The next iterations of designs, starting from figure 11, include a float support bracket that is bolted to the triple extrusion. The bracket holds the supports and also houses the load cell up top. Next is the fixed support bracket housing, which is located on the far right of the machine. It houses the fixed support, which is then also bolted to the triple extrusion. Figure 13 and 14 show the grips. The fixed grip is to be attached to the float support bracket, sandwiching the load sensor in between. The moving grip is to be attached to the linear moving housing, which is shown in figure 15 in pink. This housing holds the aluminum block that is attached to the linear guided carriage and lead screw, which passes right through it. Finally, in figure 16, we have the emergency limit switch, which was made to be adjustable on the extrusion rail. Next slide will show all the components that were ordered, 3D printed, and assembled as one. Here's the machine completely assembled and mechanically operational. Picture one shows it also connected to the gearbox and motor, which will be presented next. Picture 2 shows the fixed end support, where it is coupled to an output shaft of the gearbox that powers the machine. Picture 3 shows the left side fixed support with load sensor in between it and the fixed grip. Picture 4 here has a closer look at the lead screw, housing attachment with moving grip on top, limit emergency switch, guide rail, and carriage, all bolted and assembled to the triple extrusion below.
Hello everyone, my name is Gustavo Medel, and I had the task of constructing a gearbox for our testing machine. In order to turn rotational motion of the lead screw into translational motion of the 3D printed mesh implant, a motor connected to the lead screw must be considered. The servo motor chosen by the team has the following specifications. It's capable of continuous rotation, its peak stall torque is 30.5 ounce-inches, and angular speed can be adjusted from -120 to 120 revolutions per minute, negative denoting counterclockwise rotation. The problem with most servo motors available on the market is that they all output a low amount of torque that is not sufficient to pull 200 newtons of force. Also, having the motor directly attached to the lead screw causes unnecessary vibrations that may cause problems within the system. So a gearbox that would be 3D printed is considered for design in order to decrease the angular velocity and multiply the output torque. We now should consider the constraints of the testing machine for the design of the gearbox. Here on this slide, we can see the constraints in place for our uniaxial testing machine. Keeping in mind the constraints of the testing machine and dimensions of the ball screw kit, and by use of the principles of the kinematics of screw mechanisms, the angular velocity of the output shaft of the gearbox can be obtained and is 5 revolutions per minute, as can be seen on the slide. Since our motor can operate between 120 RPMs counterclockwise or clockwise, we will set the angular velocity of the motor to 50 revolutions per minute to not have the motor operating at full power the entire time. Considering input and output speed needed, we can design a gearbox with a reduction ratio of 10:1. Although the minimum output torque needed is 50 ounce-inches, we have 300 ounce-inches due to our gear ratio, which is more than plenty. Angular velocity is more important for a translational motion of the lead screw in this system. Now we can take a look at the complete design of the motor and gearbox assembly. Here we can see the complete design and top view of the gearbox and housing assembly. The gearbox consists of the gears and housing, which were designed using Autodesk Fusion 360, the motor, shafts, bearings, and other hardware to secure everything together, which were all purchased online. You may be wondering why we decided to 3D print gears. This is because the majority of gearboxes available online are unreliable and may also cause unwanted vibrations of the system. By 3D printing the gears and housing, we have complete control over the specs and size of the gears to make a gear ratio of 10:1. The gears themselves and the housing was designed to be 3D printed with consideration of other hardware needed for smooth operation of the system. Here we can see 2 pictures of the physical 3D printed gearbox viewed from 2 different angles, and also a brief video of the gearbox during operation at the right. I'm now going to hand it off to Carlos, who will talk about the electronics of the testing machine.
Here is a wiring schematic setup for the servo motor and Arduino connections along with the button pins used. 2 Arduino will be used for both testing components. To test the prototype at the loading of 200 newtons, a 20 kilogram tension load cell is needed with an HX711 amplifier to obtain the load cell data. Here we have the specifications of this load cell along with its schematic setup of load cell connections to the HX711 amplifier and its respective pin connections to the Arduino board. Arduino was the chosen software to run the servo and load cell components of this testing machine. Arduino is an open source program which utilizes digital and analog inputs and PWM outputs. This free software and inexpensive hardware were the right fit for this project. Based on the programming language C and C++ and given experience with Arduino, I was familiar with the coding aspect. Tasks include code for the button control continuous servo motor and an HX711 force measuring load cell code. Servo code was used to control the rotation position of the servo motor via button commands. Buttons are to turn servo motor both in the clockwise and clockwise direction, all while displaying the position of the servo motor is currently on in real time. This is useful when calculating the displacement alongside force exerted on the load cell. Code sketch is set up by including a built-in servo library, then defining pins inputs used to connect the servo and buttons to the Arduino board, declaring variables to manipulate the data to perform the required calculations and displaying the values, thus giving a proper output which will be ran in the continuous loop, meaning it won't stop unless told to with the button commands. Unfortunately, the servo was having troubles recognizing what position and degrees it was in and not accurately displaying its position. But moving forward, we will use the servo's RPM and the time it took to make that complete turn to calculate the displacement in real time. Coding the HX711 strain load cell was more tedious as it required calibration, meaning a separate code was used to find the load cell set factor. Once calibrated, the set factor is applied to the current code as seen in the slide to measure the display load applied to the test specimen. Same sketch setup as the servo code was followed by including an add-on HX711 library, then defining pin inputs used to connect the load cell via the HX711 load cell app, declaring variables to read, load, and displaying the values of the built-in Arduino monitor. Important part of this code is continuous measurement of applied forces, looping the code to display the new applied force in either direction simultaneously with the servo's RPM position until testing was complete. Next, I will pass it over to Eduardo Gonzalez, who will talk about the printed implant process.
For the implant design, we designed a prototype mesh using pore geometry manipulation. Generally, pores in biopolymer material reduces stiffness, and non-symmetric geometry pores affects the stiffness direction. The two left figures show different geometric pore designs that produce same stiffness ratio from the X and Y axis. There's multiple prototypes having different geometric pores, but the oval and diamond shape were the simplest design to change the anisotropic behavior. FEA simulation. FEA's analysis was performed using FEBio. The new Hookean model is used for nonlinear hyperelastic behavior. The model has elastic behavior under larger strains and is commonly used to approximate the stiffness of a nonlinear material such as skin and soft polymers. PLGA, which is polylactic glycolic acid, is a copolymer of PLA and PGA, an ideal biopolymer that has mechanical properties close to human pelvic tissue. The simulation was used using PLGA properties for simulation in biaxial tensile testing, providing data for the X and Y directions. So FEA results, multiple simulation tests were needed for the stress versus strain graph. The input pressure for the tensile test simulation can display the max displacement. The displacement is used to calculate the strain at the corresponding pressure. Running multiple simulations with increasing pressure input provided us with data points needed to graph the stress versus strain plot. The strains are calculated separately by X and Y axial displacement. The slope represents the stiffness in the given axial direction. The results are displayed in the table on the left, showing the stiffness values and the calculated ratio compared to the ideal pelvic tissue ratio of 0.46 with difference of 0.3%. Now I'll be talking about conclusion. So in summary, via research, the healthy uterosacral ligament stiffness range was obtained to be from 1.9 to 6.3 megapascals. The implant prototype design satisfies a stiffness ratio of 0.467 by FEA simulations. We designed a uniaxial tensile testing machine with little machinable parts. build a physical uniaxial testing machine that has adjustable motor needs and directional control. PLGA, the ideal biopolymer, was not attainable for testing. Therefore, our pending assignment is to tensile test the implant prototype with replacement materials PLA and PETG for proof of concept experimental stiffness ratio to compare the FEA simulation results. And that concludes our presentation.